Okay, thanks for the introduction. Never been to Australia, unfortunately. And thanks for to the organizers for organizing this workshop. It has been a very interesting experience so far. Okay, so I want to move this. Okay, so this is a joint work with Pavel Bochev, Dave Littlehood, and Mauro Perego. We're all at the Center for Computing Research at Sandia Labs. Just to give some context, no, it's not working. Or it's not working. Let me try again. Now it's working. Just to give some context. This is actually Sandia. So Sandia, it is the name of the lab, but it comes from the mountain, from this beautiful mountain. And Sandia means watermelon, and the reason is because at the sunset, the mountain it's not really clear from the colors of these pictures, but the mountains become pinkish. They have this pinkish color, and it's very pretty. This less pretty is the Center for Computing Research, where we work. You cannot really see our offices from here, but that's where we are. And some more pink. This is Sandia at sunrise, still pinkish, but not the mountain. And I took this picture from my house, so it's very nice. Okay, back to, I had 50 minutes, so I thought, you know. Okay, so what I'm going to talk about is a coupling strategy. It's a very general coupling strategy we're going to apply to elasticity, but this is for more general local and non-local models. And in fact, I will start to present this strategy in a very general setting for elliptic problems, so non-local diffusion and local diffusion, or local elliptic PDEs, PDE. And then I will extend the approach and show how flexible it is, and I will extend it to peridynamics and classical linear elasticity. So at this point, there's no need to say that non-local models are very popular. They can be applied to many diverse applications. This is just a list. We heard many talks on peridynamics, but we can also use non-local models for stochastic processes, jump processes, non-local heat conduction. Juan Carlos in the afternoon is going to mention something about image processing. So in this first part, I'm going to focus on non-local diffusion. And non-local diffusion operators are the non-local counterpart of elliptic operators for PDEs. In their general form and simplest form, this is how they look like. So they're integral operators, and so our functions don't need to be smooth. We don't have to be too concerned about regularity, and they're characterized by a kernel that we call gamma. And of course, for different gammas, we can have different applications. And I'll go back to this form in a few slides. At some point, this stops working. Okay, I'm going to use this. Okay, so the most important feature is that when we are in a bounded domain or in general, interactions can occur at distance. So every point interacts with the neighborhood of points and not just with the neighbors. And so in the case of material science, these models are very good when the material dynamics depends on the microstructure. So in the case of peridynamics and non-local elasticity, what we want to capture are fractures and failures. And when we use non-local models, we solve for the small-scale features so that we can capture these discontinuities or cracks in the material and so in the solution. Another application, as I said at the beginning, is stochastic processes. And in their simplest form, non-local operators can describe Levy-jump processes. A very common application, so in this case, we have, for example, a particle that jumps around the domain. And when we solve the non-local equation, what we get is the probability density function of the particle that jumps around. And one of the applications is, for example, the estimation of the exit time of the particle. So this particle is jumping around, and we want to know when the particle leaves the domain, not necessarily crossing the boundary, because it's a jump process. And once we solve the non-local model, we have the probability density function, and so we can use standard probability arguments to estimate this time. So this was just to give you another example of applications. But today I'm going to focus more on material science. So some features and some actually good points that I want to stress are that, first of all, we have now, for this kind of operators that I'm going to consider at the beginning, mathematical and numerical analysis. Mathematical analysis first, the non-local vector calculus that allows us to study these non-local diffusion problems as basically as we study PDEs. So we can have variational forms and we can use standard arguments to study these problems. And in fact, we have well-posed results for steady and unsteady problems, control problems, identification problems. And for some discretizations, we also have some numerical analysis and we have numerical convergence results, especially for finite elements. So these are all good news, but of course, non-local models are very accurate, but we have some bad news. They're very expensive, and when the extent of the non-local interactions increases, or when we have a very big computational domain, these problems can be even intractable. At the same time, we know that we can compute PDEs very efficiently. We have very good methods, fast solvers to compute PDEs. So this is just to give you an idea of how bad the situation can be, even in a 1D problem. These are finite element matrices, stiffness finite element matrices for a simple 1D Poisson equation. The first matrix is the regular finite element matrix, 3-diagonal matrix. And these are matrices as the interaction radius, as the extent of the interactions increases. So the matrices are becoming are becoming denser and denser. The bandwidth is becoming larger. And the problem here is not just in the solution. It's not just solving these matrices, it's also assembling these matrices. Because every entry in the matrix in 1D is a double integral, and the integrand of the integral can be singular. So even the assembling part can be very, very expensive. So now let's assume that we know that in some parts of the domain where the non-local effects are not too strong, we have a local model that well approximates the solution. So where the solution is nice and smooth, we have a good approximation by a non-local model of our solution, so of our model. So what we want to do is to solve for the non-local model, the accurate but expensive non-local model, only where it's necessary, and solve the local cheap problem everywhere else. Of course, the challenge is to combine the two models at the overlaps or at the interfaces. So Pablo gave a very good introduction to this problem. I'm just listing some works that have been done, some works that we can find in the literature. On Tuesday, Pablo talked about force blending and a variable horizon approach. There's a very nice recent work by Tian and Du that can be, where these new non-local trace theorems can be used to do some local non-local couplings. But again, I don't want to repeat what we already heard on Tuesday, so I just wanted to recall these few works. So what we do is an optimization approach, which changes a little the situation with respect to previous local non-local approaches. So what we do is to decompose the domain in a domain decomposition fashion. We have a non-local domain and a local domain, and we create fictitious or virtual boundaries. And what we do is to basically to minimize the difference, solve the non-local problem in the non-local part and the local problem in the local part, and then minimize the difference between the two solutions on the overlap, tuning the values of the solution on those virtual boundaries that form after the decomposition. So we solve the non-local problem in the non-local domain, the local problem in the local domain, and we're looking for the optimal boundary conditions on those fictitious boundaries so that the two solutions are as close as possible in the common volume. So this method is very general. It can be applied to any non-local and local models, actually to different non-local models. In this case, the point is we have a local model that approximates our solution where we don't have non-local effects or where the non-local effects are negligible, and so we want to solve the non-local only on those parts where the non-local effects are pronounced. And then we combine them through optimization. So one thing, first nice thing of of this approach is that usually the well-posedness of this problem follows from the well-posedness of the constraints. So when the constraints are well-posed, and when we have some additional properties that I will talk about later, this problem has a unique minimizer. Another important feature is that in this setting, we pass the patch test, which means that the method is consistent. When the two models have the same solution, allow the same solution, these two solutions coincide on the overlap. Another very important feature that it was very important for us in particular is that the local and the non-local models are completely separate. There is no interaction at all between them. So we can use different meshes. We can actually use mesh on one side and a mesh-free method on the other side. And so we can use different solvers and different softwares. This is good because we can have very good and efficient solvers for PDEs, good solvers for, in our case, PERIDYNAMICs or in general, non-local models, and we can use them just as black boxes. So there is no interaction between them. We don't have to introduce a hybrid model. And the novelty, so the difference with respect to previous methods is that we switch the roles of coupling conditions and state equations. Now the coupling is imposed in some sense weakly through optimization, while the models are prescribed strongly. So this is an outline. As I said at the beginning, I will start with a very simple problem, which is the non-local and local Poisson equation. And for this case, I will do some more rigorous analysis, mathematical and numerical analysis, finite element approximation, and some 1D results, just to see if the method is consistent, accurate, and if we recover some convergence rates. And then I will move to the same non-local diffusion, but with mixed boundary conditions and volume constraints. And I will present some analysis for this as well, and numerical results will be 3D numerical results combining a mesh-free method and a finite element method, and eventually I will switch to the non-local elasticity case. So before starting, I want to say something about the techniques that we use, and in particular, we're going to use a lot of results of the non-local vector calculus. These are the two main references for the non-local vector calculus, very long but nice papers. So basically, the main idea is that the non-local vector calculus is a generalization of the classical calculus to non-local operators. And as I said, with the non-local vector calculus, we can study the non-local equations in a very similar way as we study PDEs. I don't want to go into the details, but I just want to show you how it works and how we can use it to solve our problems. So in this calculus, we introduce non-local operators, which are the counterparts of divergence and gradient in the local case. So we have the divergence operator, which is an integral operator. Where is the... Okay. This is an anti-symmetric function. Of course, this is just an integral operator, so no regularity, no derivatives are involved. This is the non-local gradient, and it can be shown that the negative of this operator is the adjoint of the divergence. And so as we do in the local case, we combine divergence and gradient. This is just, we can call this diffusion coefficient. So the combination of the divergence and gradient operators gives what we call non-local Laplacian. So if we combine these two, this is what we get. And if we rename this thing here as gamma, we get exactly the operator that I introduced at the beginning. They're the same operators. The difference here is that this is a combination of a divergence and a gradient. And so we can write, we can do integration by parts, we have Green's identities, we can write variational forms and analyze these equations using the standard arguments that we use for variational problems. So since every point in a domain interacts with a neighborhood of points, when we want to solve a problem inside the boundary domain, when we get to the boundary, the information that we have on the boundary is not enough. So we need to introduce an interaction domain, which basically in the interaction domain, we have all the points outside of the domain that interact with points inside the domain. And this is where we will prescribe non-local boundary conditions or volume constraints. The kernels that we consider are localized kernels, which means that their support is a ball of radius epsilon surrounding the point, and we call this epsilon interaction radius. So this is some notation, the notation that we need for the problems that we consider. Okay, these are the references for the optimization approach. So first problem, Poisson problem, very simple. This is the non-local operator that I introduced at the beginning. This is the non-local counterpart of a Dirichlet boundary condition. So it's a volume constraint here. We prescribe a known function to the solution in this layer of thickness epsilon surrounding the domain. And this is the corresponding local operator. The reason why we use this one is because for some kernels that are the kernels that we're going to consider, as epsilon goes to 0, this equation converges to this equation. So it all makes sense. So we split the domain, as I said at the beginning, in a non-local domain, which is this part here, and a local domain, assuming that we know that the non-local effects are here. We have an overlap. This is a virtual boundary that comes from the decomposition. This is the virtual interaction domain that comes from the decomposition. And this is the physical boundary, where we assume that we know the boundary conditions and the volume constraints. So what we do is to minimize the difference between the two solutions inside here, and find the optimal values of the optimal values of the boundary condition and the volume constraints that are our control variables. So again, these are the state equations, local and non-local. These are our control variables. So this is the volume constraint here, and this is the boundary condition here. And we minimize their difference on the overlap. So inside, it's the L2 norm of the difference on the overlap. So once we solve this optimization problem, we find the two optimal values of the boundary condition and volume constraint. And we compute the local and the non-local solution in correspondence of the optimal control variables. And our coupled solution is defined as the non-local solution in the whole non-local domain and the local solution in the remaining part. So now that we have the method, we have to ask, we have two questions that we need to answer. First of all, is the solution unique? So is the problem well posed? And what's the error with respect? Because remember, what we want to do is to solve the non-local problem everywhere. So what's the difference between our coupled solution and the global non-local solution in the whole domain? So we start from uniqueness. To do this, so we assume that our constraints are well posed. And so we can rewrite our functional in a reduced form. So we write the functional only as a function of the control variables. And so we get this norm here. To study the well-posedness, we split the solution in harmonic components and homogeneous components. The harmonic components solve exactly the same problem with a zero forcing term. The homogeneous components solve the same problem with zero boundary conditions everywhere and volume constraints, homogeneous volume constraints everywhere, but in this case with the forcing term. And the solution can be rewritten as the sum of these two components. So once we have this splitting, we take the two solutions and we put them back in the functional. And this is the functional that we are actually going to consider. So we have a first quadratic term in the harmonic components and a mixed term in the homogeneous and harmonic components. There is another quadratic term in the homogeneous components, but we don't consider that because that's constant with respect to the control and we don't care about it in the minimization. So the main result here is that this problem is well posed, and the key point to get to this conclusion is that this norm, the norm of the difference between the harmonic components, actually defines a norm in the control space, and we're going to call this norm energy norm. And the control space is Hilbert with respect to this norm, and so we can use standard arguments to get to the well-posedness. So basically, we show that this inner product is an inner product in the control space, which is Hilbert with respect to this norm. Now, the second question was how far, so let's define this as the non-local solution everywhere. what's the difference between our optimal solution or our coupled solution with respect to the non-local global solution, which is what we want to recover. So it turns out that this error is bounded by the modeling error, which is basically the difference between a local and a non-local solution in the local domain, which kind of makes sense. So we define this UL hat as the local solution computed in the local domain, where we prescribe on the control boundary the exact non-local global solution. So this is what we would get if we prescribed the non-local solution here. So this is the bound on the coupling error. Now, with many kernels, as I said at the beginning, we can show that the non-local operator converges to the classic Laplacian. And we also have some order, and this difference is proportional to some order of epsilon. So when we are in these cases, so when we do have this convergence to the Laplacian, we can show that this modeling error is bounded by a power of epsilon. And this power of epsilon, of course, depends on the difference of these two operators. So what we have at the end is that the coupling error is bounded by a power of the interaction radius. And of course, when the interaction radius goes to 0, the two solutions coincide. So we have only a local solution.
And this C above is independent of epsilon?
Yes. To get to these results, of course, we had some assumptions. I want to focus on this part. So we also had to prove some lemmas, because whenever you try to solve to prove something for a non-local problem, you always end up needing other proofs for parts of your non-local problem. Anyway, we had to prove a non-local trace inequality, which is a little different from what we heard, I don't know if you remember, in the talk on Tuesday by Tian. The most important result, and the result that took us forever, is a strong Cauchy-Schwarz between the harmonic components of the solution. So we had to prove that we don't have a regular Cauchy-Schwarz, but the constant here is less than 1. And once we have this result, we could prove the error bounds and the well-posedness. And of course, we used many results of the non-local vector calculus and many properties of harmonic functions. For the finite dimensional approximation, so in this case, we only want to study consistency, accuracy, and so I'm going to focus only on finite elements and 1D results. Since we're considering 1D, it still makes sense to consider finite elements also for the non-local problem. This is just because we don't have the resources to, and the code, a 3D code for the non-local problem, because it's going to be very expensive. Anyway, we're in 1D, so we're using finite elements for both. Using the non-local vector calculus, you can move from the strong form to a weak form, which looks exactly the same as the local, with the difference that we have a double integral here. This is the non-local gradient operator, and as you can see, they're basically the same formulations. So we discretize both with finite elements, and we get to the discrete form. We rewrite the functional, we obtain the functional in the same way, in a reduced form, where in this case, these functions are the finite element solutions. They are not just the continuous function. And this is why this functional is different from the continuous one. So we're not just applying the discretization, we're not just substituting the discretized variables in the previous functional, but the functional is actually different. And this is important in the numerical analysis of this problem. But the structure is the same. So we want to prove the well-posedness of this fully discrete problem. And we call this norm here discrete energy norm. And basically the result is pretty much the same, in the sense that what we do is to prove that this norm here is a norm in the discrete control space, which is Hilbert with respect to the norm. And to get here, we needed to prove a strong Cauchy-Schwarz inequality. So the same inequality, and actually with the same constant, but for the discretized harmonic variables. And once we have this, the proof is exactly the same. Now, we want to do some convergence analysis. We have to keep in mind, as I just said, that the two functionals, the two problems are different. So here we have a JH because the functions here are, the solutions are discrete solutions. And the optimal condition, the optimality conditions, so the Euler-Lagrange equations are different. So these are the bilinear form and functional that come from this functional here, and these are the discretizations of them. So we cannot use standard, we cannot use Lax-Milgrom, we need something more. So what we do here is to analyze the error in the energy norm. So this is the optimal control variable in the continuous problem. This is the optimal control variable for the discrete problem. We're going to find an estimate for this norm. It's basically the difference between the harmonic components. This is not what we want to get. So from here, from this discrete energy norm, I will move to simpler norm, to standard norms, L2 and H1/2. But at first, I'm going to focus on this norm. And I'm going to use the Strang's second lemma. The reason why we use this lemma is because it's the one that requires, that doesn't require too many assumptions on the solutions and on the operators. Because when you have non-local solutions, you don't want to require too much regularity in your results. So to apply this lemma, what we need is that this discrete bilinear form is continuous and coercive, but we do have this because we proved the well-posedness. And we have to have some relationship between the discrete energy norm and energy norm. And we do have both of these assumptions. So it turns out, so when we apply this lemma, basically what we have to estimate are two terms. The first terms is just a matter of approximation theory in the discrete control space. And then we had to evaluate the difference between the discrete bilinear form and functional. For some equivalence properties of the energy norm and discrete energy norm, it turns out that the first term is 0, so we can disregard that. And the second term, it's kind of messy, but basically what we have here is that the second term is bounded by the difference between discrete and continuous solutions. So non-local, discrete and continuous, local, discrete and continuous, and it's all the same. So what we can do is to use finite element results for the theory of finite elements or interpolation in Hilbert spaces and get the usual convergence rates in terms of the local discretization step and the non-local discretization step. So this is the standard finite element estimate for in the local case, and this is, again, this is standard for the non-local case. So here's what we have. When we put everything together, this is the estimate, the bound that we get in terms of Hn and Hl for the discrete energy norm. But from here, we want to go to some standard norm for the non-local control and local control. So we take the L2 norm here and the H1/2 norm here, and here are the estimates that we get. Now, we don't want to have a bound only for the control variables, but we want to have a bound for the state equations, for the state variables. And we use this norm to bound the state variables too, because we can claim that the difference between the states is bounded by this. The problem is that if we do that, we do get basically the same convergence rates. The thing is that they're not optimal, because in the non-local case, we're losing a half order of convergence. Anyway, when then we run the computational results, we see optimal convergence rates. So probably this bound is not, though valid, is not sharp. So maybe to get the convergence rates for the states, maybe we should go from some other way. But it took us forever to get here, so we were happy with this. The results in 1D, this is the domain that we consider. So here we have the non-local domain, and this is the local domain. The green part is the overlap. This is where we have the local control variable, non-local control variable. And so what we want to do here is to do a patch test, and we do pass a patch test. We prescribe a zero forcing term, and what we want to observe is a linear solution everywhere, and this is what we get. But I'll show patch tests for the 3D results because they're more interesting. And we want to find convergence rates. So we prescribe, so what we compute here is a quadratic function for both the local and the non-local problems, and a cubic function, because up to the third degree, the two operators behave basically in the same way. So a quadratic function and a cubic functions are solutions of both operators. And so we have an exact solution and we can compare it with the discrete solution that we get. And as you can see, these are the rates for the non-local state, local state, and non-local control. And in this case, we're using piecewise linear finite elements for both, discontinuous for the non-local, and we get a quadratic convergence in the L2 norm. So that's why I was saying that probably the bound that we found is not sharp. So enough with 1D. So we're going to consider a little more complicated problem. Basically, what we're going to add is another volume constraint. So in some parts of the interaction volume, we're going to consider Dirichlet boundary conditions as before, volume constraints as before. And here, we consider the non-local counterpart of a Neumann boundary condition. And the reason why we want to do this is because then when we move to realistic problems, we don't have just Dirichlet boundary conditions. We do have, especially when we consider peridynamics, for example, we want to prescribe stress conditions. So we need to study this problem as well. And the local problem that we consider in this case, the one that we use for the coupling, is again a Poisson equation, but with mixed boundary conditions. So a Dirichlet condition and a Neumann condition here. The problem is exactly the same. So we proceed in exactly the same way. We minimize the difference on the overlap. The difference now is that, the difference with respect to the previous problem is that here we have Neumann boundary conditions. And this changes the analysis quite a bit and makes it a little harder to get to the well-posedness. But again, the structure is the same. So we minimize on the overlap, and these are the new constraints, which are the same with the additional Neumann condition. To prove the well-posedness, we write the functional in a reduced form. We proceed with the splitting, and again we can prove that this norm is a norm. This difference is a norm in the control space. But to get here, we had to prove some additional results, including a non-local maximum max principle. But anyway, using these tools, we could get to the well-posedness of this problem, and so even in this case, we have a unique solution. Now, when we get to the discretization, since we want to move to 3D problems, we don't consider finite elements. But this is why we think that this method is very nice. We don't have to stick to the same discretization method for both the non-local and local problem. So we're going to use the particle method, the mesh-free method here, and we're going to discretize the strong form, and we're going to use finite elements for the PDE. So since we use this particle method, basically we have, and Pablo described this very well in his presentation on Tuesday, we discretize the operator in this case and not the weak form. So we go by material points. So this is the neighborhood of a material point, and this is how we approximate the non-local operator at one material point. And of course, we need to redefine the functional, because our functional is an L2 norm, which is continuous, and in this case, we cannot just use the functional, but we consider a pointwise difference between the two solutions on the overlap. So basically, we evaluate the difference of the two solutions at every material point on the overlap. And so this is basically an interpolation. It's an evaluation of the local solution at the material point. Numerical tests, commercial. These are the softwares that we use. They're all developed at Sandia. This Paradigm is a software for peridynamics, which in this case was adapted by Dave to non-local diffusion. So from vector to scalar, because we are considering a scalar here. Albany is a software for the solution of PDEs using finite elements, and Roll is part of the Trilinos package, and it's a rapid optimization library that we use for optimization. So the main point here is that we have these efficient solvers for peridynamics and for PDEs, and we can just use them as black boxes. No modification required. We just prescribe the control. We just give the control variables, and we get the values of the states, and we pass everything to the optimization solver. This is an example of the computational domain that we use. So we have the particles here. This is the non-local domain. This is where we know the boundary conditions, the volume constraints. Same here. This is the non-local control domain. This is the local control boundary. And this is the kernel that we use. So the first test is the patch test. We have a zero forcing term, and what we want to observe is a linear gradient. And this is exactly what we get here. It's a linear gradient along the domain. And maybe you cannot really... So from here, you can see that this is just a slice. This is just a part of the domain, and we do have a linear. The blue dots are the non-local solution. So we do pass a patch test. Then we want to do something more realistic, so we prescribe in the domain a crack. So we have a crack here in the geometry. And when we have this situation, what we want to do is to solve the non-local model only around the discontinuity and solve the local model everywhere else. And it would make more sense to have something longer here, but this is just an example. So here we prescribe, again, zero forcing term. And what we see, but I have a better picture later. So here we have a smooth solution. It's a gradient again. And here we have a jump in the solution. So this is what we want to obtain, basically. We have the non-local accuracy around the crack. So again, this is just a slice. We catch the jump, and then we have a smooth solution everywhere else, and we can solve with the finite element. We can use the local model and use finite elements. So luckily, there were presentations about this model here. We can move to PERIDYNAMICS, and I'm not going to say too much about this. The structure is the same. As you can see, this is a force state field. We're dealing with vector variables, which describe the displacement of our points. We consider the linear peridynamic solid that John Foster derived during his presentation, and this is the force state field that we have. We consider a linearized linear peridynamic solid because we have a linearized non-local dilatation. So what we do is to use this T in our operator, and this is the non-local equation that we have. The non-local operator is the linear peridynamic solid. This model has two important features. For a quadratic displacement, that non-local model basically reduces to the Navier-Cauchy equation, so the classical linear elasticity equation. And when epsilon goes to 0, that model converges to this model, so to the linear elasticity. So this is the local model that we consider in our coupling strategy. Again, the optimization problem is defined in the same way. So we have, in this case, the linear peridynamic solid. This is our control variable on the control domain. And this is the linear elasticity equation. We minimize the difference between the two solutions on the overlap. So nothing new here. We use finite elements here, finite element method here, and we discretize the strong form here using just material points. And again, this was covered in previous presentations. And it's not fundamental here. This is an example of the computational domain that we use. I wanted to put this just to explain how things work. This is the non-local domain, and this is the physical boundary where we know the boundary conditions, the volume constraints. The reason why we have different colors is because we want to prevent the bar to rotate and translate. So we fix these points in this direction, and we fix these points in this direction so that we cannot have rotation or translation. And this is the local domain with the same conditions here so that the thing doesn't move. The first test is a patch test. This is the solution that we want to recover. We have a zero forcing term, and what we have is that all over the domain we have a linear solution. And again, from a slice, you can see this better. So we have a perfect match here. Since, as I said before, the two models coincide for a quadratic displacement, we consider a quadratic solution just in the first component of the displacement. And, well, this is the corresponding forcing term that we have to use. These are some physical parameters, and we are using here stainless steel. And what we get is that we have exactly the quadratic solution everywhere, and in particular on the overlap. So we're passing a patch test, also in the quadratic case. So the method is consistent. This is a similar mesh as before, similar computational domain. We have a crack, we pre-prescribe a crack in the domain. We want to solve the non-local model around the crack and the local model far from the crack. This is magnified. It's actually smaller using these parameters, but just for you to actually see the crack. We're prescribing here local boundary conditions. So we prescribe two opposite displacements. And this is what we get. The nice thing here is not just that we're solving the non-local problem around the crack, but it's also that we're only prescribing local boundary conditions. And this is very good. This is what we want to do, because we're never really sure of how to prescribe non-local volume constraints or boundary conditions. So here we can just use regular local boundary conditions. And again, this is basically along the crack. So this is the line here, where we capture the discontinuity. Last test, so this is a tensile bar. The non-local behavior is concentrated here, so in this tiny part of the whole domain. This is the computational domain. Here we have a finite element mesh, and here we have the material points. What happens here is that, so here we still have the finite element mesh. This is the overlap, so this is the local control nodes, and these are the non-local control nodes. And let me go straight to the crack. When we prescribe a crack right here, this is the solution that we have. So this is Y. So when we look at the Y displacement here, you can actually see that the displacement is going in the opposite direction. And what is happening here is that we're prescribing displacement going down here and up here. And so this is what you want to observe. And this is a perfect example of what we want to achieve. So this is very small. And of course, computing the non-local solution everywhere there is not affordable. So we focus only here with the non-local model, and we solve the finite element everywhere else. Now, of course, there's a lot of work, still a lot of work to do. Right now, we're doing accuracy tests for this method. We want to make sure that our solution is converging, how it's supposed to converge. For now, we only have a consistency test. And then we want to improve the performance, because this is a very nice method, but compared to other coupling methods, this is optimization. So we have not several, but we do have iterations. So it's more expensive than other coupling methods. So we're working on it. And of course, we want to move to unsteady problems, because that's actually what you want to simulate. But of course, again, since we're using optimization, this complicates the things even more, because optimization in time is more expensive and more complicated to analyze. I'm basically done. Before concluding, I just want to mention a workshop, a non-local workshop that I'm organizing with George Karnadakis at Brown. This is going to be in December in Santa Fe, New Mexico, also very pretty. It's the second week of December. The main goal of this workshop is to combine two non-local communities. So the fractional community and like the material science non-local community, or the more general community that considers finite interaction radius. Because these two communities have a lot in common, but they probably don't communicate enough. So the idea here is to have at first a course, 2 days course, where everybody learns pretty much everything, so that we have all the same preparation for the workshop. This is the scientific committee. 2 of them are here. 1 couldn't come. These are some confirmed course lecturers. Pablo is one of them, and these are some of the speakers that we're going to have. We're going to have poster sessions for students and postdocs. I'm going to send emails to some mailing list about this, but if you want to tell your students, that would be great. And I'm done. Thank you.